All right, now we have two final examples that deal with kinetics and kinematics. So in this example, we've got a vehicle that weighs 300 pounds. A brake force of 1,200 pounds is applied to the vehicle as it moves down a 5-degree slope. And it's moving down at 50 miles per hour, which is 73.3 feet per second. And it asks, what's the distance required to stop? And so the steps here is we're going to draw our free body diagram, right, our FBD KD. We're going to then choose equations of equilibrium to apply. And if necessary, we're going to use kinematics. And then we're going to look to solve our equations. So take a look at our FBD KD. Right, I've got this car moving down a slope. There's 5 degrees. I've got the weight. I've got a normal force from the road. And then I've got the brake force that's applied. And over here on the KD side, I'm going to draw my vehicle, and I'm going to draw the mass times acceleration. And I'm going to put it in the positive x direction. It may end up going in the other direction, but I don't have to worry about that right now. And so I've got my coordinate system as well. I've put a tilted coordinate system lined up with the slope, the 5 degrees. So I'm just going to apply some equations of equilibrium. I'm going to sum forces in the x direction. So on the left-hand side, I've got minus 1,200 pounds. I've got plus the weight times sine of 5 degrees. Nothing else working, right? It's just that component right there. On the right-hand side, I've got the mass times the acceleration in the x direction. If I sum forces in the y direction, right? And again, remember the y is tilted. So I'm going to sum forces. I've got the normal force. I've got minus the weight times a cosine of 5 degrees. And over on the KD side, I've got 0. So I've got the ability to go ahead and solve for, the acceleration. And so we're just going to use that first equation. That's going to tell me that mass times acceleration. I'm just going to redo this, minus 1,200 pounds plus it's a 3,000 pound vehicle times the sine of 5 degrees. And I've got the mass right there, which I'm going to use here in just a second. And it's going to tell me that AX is equal to 1 over the mass of that quantity of minus 1,200 pounds plus 3,000 pounds times sine of 5 degrees. And so if I do that math right there, I'm going to end up with the acceleration equal to minus 10.07 feet per second squared. So I find out that thing's going to be a constant. Right? Got the answer right there as well. So now I'm asked how far, right? We're asked what's the distance required to stop. So let's kind of take a look at our inventory here. I've got a constant acceleration. Right? I've got, from a distance point of view, how long to stop. I'm going to say I start at x equals 0. X final, that's my question mark. That's what I'm going to find out. I know that my initial velocity is going to be equal to 73.3. And I know my final velocity is going to be equal to 0. That's when I've stopped. So I'm just going to go ahead and put that in my kinematic relationship with acceleration and velocity. So I'm going to end up integrating this from xi to x final. I'm going to integrate the right-hand side from vi to v final. Vi is equal to 73.3. V final was equal to 0. X initial was equal to 0. And so this is going to give us a kind of a nice times x. I'm going to evaluate that from xf to 0. Over on the right-hand side, I'm going to have 1/2 v squared, 0, 73 0.3. And so just one more step, minus 10.07 xf, which is going to be equal to 1/2 0 squared minus 73.3 quantity squared. And so if I just go ahead and solve that, I end up with a answer for xf of takes about 267 feet for that thing to stop. All right, our last example here, we've got a conveyor belt delivering a crate, right, to the ramp at A such that the crate's speed is 2.5 meters per second directed down the ramp. If the coefficient of kinetic friction is equal to 0.3, determine the speed at which the crate slides off the ramp. So that's what we've got here is a conveyor belt right there. So that conveyor belt is going to deliver the crate right to a ramp, and that crate's going to slide down the ramp. And so we're asked, what's the speed right down there? So we've got a couple of things. We need an acceleration, and we're going to find that acceleration from an FBD KD. So let's go ahead and take a look at drawing at 30 degrees. Let's draw it when it's on the ramp. Let's draw our FBD KD for the crate. So I've got the weight of the crate. I've got a normal force from the ramp. And I know that it's sliding down. So I've got a force of friction, which is equal to mu k times n. Over on the right-hand side, I've got the mass of the crate times the acceleration. I'm going to use a subscript x. I'm going to tilt my coordinate system. So I'm going to align the x-axis with the ramp, putting y perpendicular. And so let's go ahead and apply some equations of equilibrium. If I sum forces in the y direction, I end up with an expression for the normal force, which I'm going to use when I sum forces in the x direction. And again, just remember that the x is tilted. So if I sum forces in the x direction and I call down into the right positive, I end up with minus the force of friction. I've got plus the weight times sine of 30 degrees, and that's going to equal the mass times the acceleration. So I'm going to just kind of manipulate this and end up with an expression for the acceleration. That's going to equal minus force of friction plus the weight times the sine of 30 degrees divided by the mass. And so at this point, I'm going to then put in the expression for the force of friction. So it's minus mu k n plus weight sine 30 degrees. Right, that whole thing over m. And I'm going to kind of try and keep it symbolic here. And so I've got minus mu k n up above is the weight cosine 30 degrees plus weight sine 30 degrees, and that whole thing is divided by the mass. And so I'm just going to have to plug in my values here. I know the weight, right? I've got the mass is equal to 12 kilograms. I'm going to define the weight. I'm going to have to multiply by 9.81. That's going to give me newtons. And if I just go ahead and plug all those in, I end up finding that the acceleration is going to be a constant, and it's going to have a value of 2.356. And so what we're asked for is the velocity down there at the bottom of the ramp. So if we put position equal to 0 at the top, and we know that ramp is 3 meters long, the initial velocity we're told is 2.5. And so then we're asked to find the final velocity. And so we've got a pretty handy equation, right? I can do A ds is equal to V dV. And so I can go ahead and put my expression in. I've got integration limits that I'm going to use. I'm going to put my acceleration in there. On the other side, I've got integrating from the initial velocity to whatever the final velocity is. And if I just go ahead and integrate and evaluate, then this ends up being 1/2 v final squared minus 2.5 squared. Over on the left-hand side, it just ends up with the expression that you see right there. And so all we've got to do then is just do the math, take a square root, and we'd end up with a velocity of about 4.52. And so a little bit of reflection, does that make sense? Is that a decent answer? Well, I've got the fact that the final velocity is, well, greater than the initial velocity. So at least that makes good sense, that I can rest assured that at least it's speeding up, which it should be doing because we had a positive acceleration.